Thank you. So this is kind of a logical continuation of the last speaker, so thanks for introducing the theme here. I'm very happy for that. So I'll talk about our efforts in Lund to continue in this direction. So the outline is, I'll first present status of the 3.5 nanowire TFETs to what we've been doing in Lund. I'll talk a bit about the variability in statistics in our devices, and then I'll briefly talk about where are the defects and how are the different defects contributing, what do we learn from our data. Then I go over to a section talking about the band tails, and I'd phrase this the myth, and then we look into the data, what do we have, and then we come up with a model, how can we interpret and understand the band tails, what they are doing. Then I come with the conclusions in the end. So I'll start by talking of the method that we used to process this. So we use the VLS growth method. The benefit of this technique is that we have a wide flexibility in the material combination, so we can combine materials with different lattice constants. We're not limited by this. So here we're showing, for instance, in this case, it's indium arsenide. We use gallium arsenide and timonide now as a source, and then there is a gallium and timonide at the top contact. So we demonstrated actually, and we published last summer at the Silicon Nanoelectronics Workshop, working devices with 11 nanometer indium arsenide diameter, right? And it's not a MOSFET, and I'm not sure that we gave the transconductance, but at least we published the IV of this one, so it's working. But the technology is very similar to what you're using at MIT and also what's used in Japan. So the status roughly is this. If we take data processed in Lund for here is an indium arsenide MOSFET to the left and indium arsenide TFET in the middle, and then we just plot the IV of these two devices and we compare it. So we see that roughly we're approaching 60 millivolts per decade for the MOSFET as well, and then when we do the TFET, we go below, so we're well below 60 millivolts per decade. And we see the benefit of the MOSFET at reduced gate overdrives. We have an increased current for a TFET as compared to the MOSFET. However, when we go up at higher biases, of course, the MOSFET is winning because we're limited by the tunneling junction. So this is exactly what you would expect for a TFET, and this is also what we observe. I also include some of the benchmarking data that we published last year at IDM. Looking into the red, this is data point for our TFETs. We picked some literature values for silicon MOSFETs, etc. They are here in cyan. This is 60 nanometer FinFETs from TSMC. The pink here is actually a 20 nanometer SOI technology from IBM. And exactly we see the same thing here. At low drive voltages, 0.2, 0.3, actually we have a higher drive current than what we found in literature. I'm not saying that this is really general true. There might be better data out there. It's really hard to find the best one. Maybe the industry is not publishing their best data, but this is actually what we found. So in this case, actually, at least we're competing with state-of-the-art silicon technology with a 3.5 TFET. Then also some more metrics. The sub 60 millivolt per decade is operating at, in these ranges, 1 to 300 nanoamps per micrometer. So we have about bit more than 2 orders of magnitude. The steepest slopes is about 48 millivolts per decade, in this case at 0.3 bias. And we reach an I60 of about 0.3 microamps per micrometer. So this is roughly state-of-the-art, the best devices that we made. Then comes the statistics of this one. So we plotted on a wafer. We plotted now transfer characteristics of about 10 TFET devices. It starts to look like this. It looks, of course, like a jungle. So there is a variation of this one. So I was first very worried about what's happening of this. And I was very pleased to see the calculations from Peter Aspekt's talk yesterday to see what are the individual dopings doing to this variation. However, it turns out that the variation is actually much less than what than what we are seeing here. So it looks like we could have effects of processing, variation in work function on the metal, etc. that's contributing. The good news is, though, if we just adjust for the VT shift of this one and say, take this away, and we plot them on top of each other, the good news is that it's quite consistent, actually, at least in the off state, and this looks pretty good, actually. And to me, this was remarkable because I would expect this to move around and to be scattered all the different ways, but this is consistent. And also, if we take a look at some of the yields that we're having, etc., if we define the yield as an operating device with a slope below 60 millivolts per decade, we characterize this and we take a look at it. We have 1 nanowire in the array, 2, 3, 4, etc., increasing the numbers sitting together. We can see that for 1 nanowire, at biases of about 0.1 or 0.2, there is a yield of 80% in our university process. As we increase the nanowires, of course, it's decreasing because there is some statistics into this, some variation, therefore it's being reduced. And also, of course, if we go up to 0.3, it's gradually reduced. I think that this is fine and this is to be expected. I think this is, again, good news. This is what we can deliver out of a university research lab. And I would say that the statistics of this one was actually measured on a sample with 88 transistors in total. And out of those, 80% were working with 60 milliwatt per decade. So what can we then learn from statistics? So we made the following plot. We take a look at what is the on current we're getting at the fixed off current of 1 nanoamp per micrometer as a function of the minimum subthreshold swing. So we can see at 0.5 volt drive voltage, there is what I think a quite clear correlation. So in this case, if we are reducing the slope, the current will increase. If we take this at 0.3, it's harder to find this correlation. The data is much more scattered, etc. So we were first a bit worried what's happening here at the higher drive voltage. Then you take the next correlation. So instead you take correlation between the transconductance of these devices with on current again. We see at 0.1 volt, not really correlated. At 0.3, very strong correlation of all the data. Now this makes a lot of sense. If we operate our devices here as off state, we go up 0.1. It's the slope, only the slopes. We're not even above I60. And this is why the slope determines it. The moment we go to higher biases, the on state is actually the one that is determining the performance. So this is also an indication to optimize the performance of these devices. We should work on the on state. The GM is really, really important. So how does this work then? What is the material we're using? So we have, as we grow this with the VLS growth method, there is a little trick in nature, and that we do a phase transition in the crystal structure. So we have tuned the indium arsenide to be a wurtzite down here. As we introduce antimony into the growth system, it doesn't like to grow in wurtzite crystal structure, so it directly transforms into zinc blender. So there is a structure with this indium arsenide and then zinc blender. So we characterized lots of heterostructures with a composition along this. So there is a grading of this transition in the material. It's a slowly varying composition over about 20 nanometer. So this sounds to first to be like a really bad structure for a TFET. But maybe it's not so bad at all. And also there is a very strong strain field. If you take a look in this TM, there is a huge strain field building up here. Because this is about 20% antimon, 10% indium. So this is almost gallium arsenide. So the heterostructure is almost indium arsenide to gallium arsenide. And I think this strain field is actually playing a role in this, in how it's working. So if we put this together, this is the heterostructure that we came out with and used for modeling to describe all the IV characteristics. So if we put this in and we do TCAT modeling, this was done at ETH in Switzerland, Andreas Schenk and his group. They were able to perfectly reproduce all the experimental data as a function of temperature, etc. And I think this is really good because it's an indication that it's working the way we would expect. But what's also interesting is that now we can turn off different mechanisms and see how are they contributing. So their finding is that if this is what we would expect if there were no traps in the system. They think that there is down to described by one individual bulk trap sitting in the core of the nanowire channel, acting as trap-assisted tunneling, then you would get the green. And their conclusion is, well, it must not be one, but we can describe it as one. It could be a discrete number, a few, maybe 3 or something like this, depending on the position. But this is the main cause actually of the IV. If we instead would take oxide traps, the DIT everybody's talking about, well, of course, there is an influence. We will shift it again, but it won't explain the data. And again, I think this is an alignment with also the work from Peter Aspect and the group in San Diego, that there is a shift in the potential. We have a potential shift from the DIT, but it's not really a trap-assisted tunneling, but it's the potential that we're shifting. And this is consistent with this picture. So our conclusion is that the oxide traps has vanishing effect, besides the electrostatics of this one. We also looked in some data in some IVs, as we heard about the random telegraph noise, and we saw actually these jumps coming up, and this is the data for a device where we actually saw 2 jumps. In some cases, sometimes we have 1 jump, in many cases no jump, but in this particular one we had 2. And the interesting point I found is that we found that the slopes were actually parallel, even though when it's jumping. Of course, there is a slight change in the electrostatics, so it's not 100% parallel. But basically, we're shifting the IV as we jump. We have single electron charging. So 1 jump, 7 millivolts. Another jump in this device, 8 millivolts. So we can think about this. 2 charging effects in this device, we have lost 15 millivolts, right? And I think this is a killer, right? Because we can't have devices where we lose 50 millivolts just because there are defects within the oxide. So we can take the time constant, so we can evaluate this defect we think is sitting 2 nanometer into the high K dielectric. It's tunneling in and out because the position is bad. But still, it's working. Then we come to the next one, the band tails. This has been a mystery, I think, for a long time, and this has been confusing us in Lund for a long, long time. So there are arguments that saying that excess current in a circuit diode, they can be described by this one. So this is basically the tunnel. You have the tunneling probability, the statistics here, and then you just take, maybe you could take an exponential decaying function. We can discuss if it's an exponential or what it is, etc. And you will get it out. And there is a huge literature where people have looked into circuit diodes, trying to see what is the conductance slope and discussing band tails, etc. on this. So we took our devices. So this is a NDR region from a transistor. Make sure that we were measuring it in such a way there were no oscillations. Took the oscillations away by careful measuring techniques. And we evaluated 62 millivolts slope here, conductance slope. And I should say this is a pretty good diode. I think the peak to value ratio of this is above 10. So it's a good diode. So this is bad news, right? Because they will say that this will never work as a TFET. On the other hand, it's quite good because it's much lower than what we find in the literature. So we take a look in the other direction, measure the slope. So the slope is 46 millivolt per decade. So now there is a mystery here. We find in most of our devices, or many of our devices, actually that the slope is lower than the conductance slope. So what is this? So my colleague Eric Lim came up with the idea, let's use this equation and derive what is the slope if we just take this equation. So you take this equation, you calculate the slope. It turns out that there is a new prefactor coming up. So it's 2.3 kT E0 divided by kT plus E0. And then we have the DIT term. So we took all our data again and plotted the slope, minimum slope versus E0. So of course it's scattered, etc. But it follows quite nice, this equation. This equation is exactly what we're deriving here. And now we just put some DIT in. The DIT is corresponding to about 2 times 10 to the 12. Not a large number, but still. So we can see the DIT here cost us about 10 millivolts per decade, which I think is reasonable when we talk about this DIT level, etc. But this equation is quite interesting. So we can say if E0 is much smaller than kT, the slope will be proportional to E0 down in this region. But if E0 is larger than kT, S is proportional to kT. But it's lower than the thermal limit because we are lowering with E0. So we have an internal mechanism where we use the distribution of the band tails actually to bring down the slope. This is what we think. So then the question is there a temperature dependence in the slope? So we followed all our devices over a wide temperature range here. So we can say, yes, there is a temperature dependence, going all the way down to 4K. Interesting is that the conductance slope is independent of temperature. And this is, again, I think, a good news because it means that if this is limited by the band tails, this cannot be a thermally activated band tails. It must be something that is not thermally connected, but we get the thermal exit by thermal excitation. So the band structure that we are starting to model here is that, suppose that we have band tails sitting here. We can think about in a TFET, they will act as a regeneration current here. If we do the Esaki diode, we reverse it, we take a recombination current instead, right? We bias this in a different configuration. Part of the story why it's not agreeing in the two directions also, these are two completely different systems because the statistics is different. Here are lots of carriers, there are very few carriers. I think we're intermixing a lot of things when we're comparing conductance slopes and slopes in transistors. Nevertheless, this can explain actually the mechanism for what's happening. Then also we did the final experiment. What if we now make an Esaki diode out of this? So we introduce doping here on the N side as well. Well, we know what's happening if when we're introducing doping in an Esaki diode. So the leakage current in the valley goes up. So there is a stronger leakage. So the conductance slope is increasing, right? And now we get the bias dependent in the conductance slope again. You can see here, this is not the case if we don't have doping here. Suddenly it starts to be a difference here. And the subthreshold slope is increasing. We're never getting below 60 millivolt per decade when we put doping in the channel. So maybe what we think is happening, impurities is one source of the band tails. I say impurities, dopants, shallow dopants. So the binding energy that we have for zinc in gallium antimonide, gallium arsenide is about 20 to 30 millielectron volts. They could be potentially screened the potential with a Fermi level. When we're moving here, this could explain this effect because we change the potential as we move the Fermi level here. So our conclusion here, P plus, N plus diodes, they are not good references, so we stop looking into this data more in Lund. And then we took this and just put it together, right? This equation. Now we can actually describe both the Esaki diode really well and also the TFET. I would say it's a remarkable good fit just for being a very, very simple model. So I think this is an indication actually that this mechanism is working. So this is our latest contribution to the field. So in summary, R35 nanowires TFETs, we are consistently delivering now below 60 millivolt per decade. So we're doing carefully measurements in Lund, offsetting dopings from the heterostructures, changing compositions in the heterostructures, going through all the processing and collecting data on this and see how is this developing. And I think this is the hard work that needs to be done to take it to the next level to understand what can be done. Our conclusion is that the drive current, ion, which I think is the metric we should talk about, really, we're limited by the slope if we are low VDS, but our devices are limited by GM, the transconductance, if we go to 0.3 volt. This is what we have to work on, the transconductance. Well, I would say they are not so sensitive to defects. Quote mark. Our devices, well, if we talk about this one, the DIT is above 10 to the 12. There are traps in the channels. We see that we have band tails. Still, we're well below 60 millivolt per decade. And the drive currents are better than maybe what you can get with silicon device. So the band tails, well, we just made a model and describe it all, putting it with a new model. So with that, of course, I would like to thank all the colleagues in Lund that are contributing. There are a number of students, in particular Elvin, spending hours in the lab fabricating these things. Marcus is doing a great job in the measurement. Johannes has been growing all the structures, and Eric Slind has been helping out with the modeling. So, thanks for your attention.
Thanks very much, and we'll start the questions.
Yeah. I wonder if you can go back 2 slides, and you had the model. Yes, there at the bottom of the slide. So in this model, the band tails are supposed to be represented by the exponential?
Yeah.
Is that right? And the TRs are supposed to be some transmission function?
Exactly. I'm sorry, there should only be one. I see there's a typo.
There should only be one. Okay. Yeah. Clearly the band tails are an issue. I mean, we need to know what E naught is. And so that I think that's important. But also with regard to the transmission, if the nature of the biases are modulating the transmission probability, that could also be a different explanation. How did you model the transmission?
So, well, actually, we're just
Did you take a constant transmission?
we're saying that it's a constant. However, we thought quite a bit about it, and what we think is actually that we're underestimating E0. E0 might be larger. If we would take the tunneling length modulation, or what we call it, into account, this will actually push E0 to be even larger.
Which is not good news.
It's not good news, but it's still good news because from this one, right? Because we're not sensitive to it, and this explains why it's working.
This is a great talk. Thank you. Just I want to clarify one thing. You said PN junction is not great to characterize. Do you mean any diode is useless, or the PIN would still be useful? The doping effect that reflects what normally a TFET already has versus PN. I understand the statement, it's a different junction than you really have. But PINs, you already have a PIN in a TFET.
Well, I think one has to be really, really careful here about what we're saying. I can only refer, and this is what we say, it's based on our devices, because our growth method is also based on gold. There could be more segregation, etc. It could be a different story when you grow this in planar structures with an MB, etc. But this is based from this, from our conclusion, it looks like the way to go for us is go for the transistor instead. This is what we need to do, at least.
Thank you.
Okay, I think we're going to move on. Thanks for an excellent talk.